This simulation is going to help us to understand the difference between transverse waves and longitudinal waves. So we're going to start with transverse waves. So here I'm going to disturb the system like this, and when I let it go, you see that the charge, these points here, they vibrate up and down, and they vibrate perpendicular to the length of the string. So whenever you have a vibration that vibrates perpendicular to the length of, for example, here the string, then this is going to be called a transverse wave. And for light, it's similar. The light vibrates up and down as it moves side to side. So here, the vibration is perpendicular to the direction of motion. So we're going to go, this is called a transverse wave. Now let's go ahead and look at the other case. So here we're going to make them vibrate. So let's go ahead and look at this case here. Let's stop it first. So if you notice here, now picture these to be air molecules, and you're creating sound with your voice. So what's happening is that in some places the air molecules are compressed next to each other, and in other places the air molecules are more spread out, so they're rarefied. And so let's go ahead and run this to see how this looks like. So you notice here that these charges are, these air molecules, they're vibrating back and forth or side to side, but also the wave is traveling side to side as well. So the vibration here is going to be along the length of this string here. So these are called longitudinal waves. So transverse waves, they vibrate perpendicular to the direction of motion. And longitudinal waves, they travel in, they vibrate in the direction along the direction of motion. And so these longitudinal waves, they can be represented as sound waves. So this is how sound waves travel from your voice to somebody's ears. And light vibrates in this direction, or vibrates like this. It travels like this. So it sends electric fields that vibrate up and down, and those electric fields travel into your eye from side left to right. So here we're going to look at some basic components of waves. So you have a wave traveling down the string here, or the slinky. And waves can travel in two different ways. So you have the length of the string. One way that the wave can travel is perpendicular to the length. So up and down like this, and that would be a transverse wave. Another way that a wave can travel down a slinky is, this is the length of the slinky here. And you're still going to get a vibration, but here the vibration is along the length of the slinky. So this would be a longitudinal wave, which is how sound travels. So you see here, the sound mimics how a slinky works, or sound waves. Just like with a slinky, you compress the slinky, and that compression travels along the slinky, even though the part of the slinky that you held here stayed where it is. It's the compression or the disturbance that travels down the slinky. The same thing, these air molecules are really going to stay where they are. They're just going to vibrate a little. So this air molecule is just going to vibrate a little, that one there a little. But what's going to travel down the pipe here is going to be the disturbance. And you're going to perceive that to be sound. So here this shows you that any two repeating points, in this case for a sound wave, that's going to represent the wavelength here. So another thing is, how do you perceive something to be high pitched or low pitched? If the distance between any two repeating points is small, then that's going to correspond to a high frequency. So this would be, for example, in the kilohertz range. And if the separation between any two repeating points is really far apart, and this would be a low frequency or low pitch. So this concludes the second part of the lecture for chapter 16.